make this formal on announcement first. Okay. As you all know, midterm will be on the 24th, right? Sorry. 1 to 4 p.m. Okay, 1 to 4 p.m. Okay. Um, you can bring in non-programmable, non-graphical calculator. Okay. If you bring in programmable calculator, it will not be allowed to the exam room. Okay. And the cheat sheet that you have to prepare can only contain notes that are handwritten. Okay. Electronic writing is not around. Okay. Printing is not allowed. Okay. It's important to bring a pen. Okay. A working pen. Okay. Make sure you write your final answer with a pen, because otherwise, if you write it with a pencil, it may fade. Okay. Bring a ruler as well. So write legibly with a pen. Okay. If I cannot grade, okay. If I cannot read, then I cannot grade. In terms of distributions, okay, there will be 45 questions, okay, multiple choice, 38, 1 point each, and the distributions are according to that. Okay. Hey, 1 second, 1 second. Sorry, 1 second. Sorry, I got this wrong. So it's gonna be something like this. 1 second. 12. Okay, 1 second. Yes. So now it's correct. So for multiple choice, it will cover all the topics that we study. Okay. Including queuing theory. Okay. There will be some multiple choice question for queuing theory as well. Okay. So 10 for the introduction. Okay. 14 for wireless and mobile networks. Okay. 12 for 5G. Okay. And then 2 for queuing theory. Okay. And in addition to the multiple choice questions, there would also be essay questions, right? 7 of them. Okay. Totaling 6 points, 30 points, and 26 points respectively. Okay. To study for your material, please go over all the lecture slides, recordings, okay, and quizzes. Okay, there is one quiz today. There will be another essay homework at the end today. And in addition to that, there would be some practice problem for the midterm to be released today as well. Is there any question, comments about the midterm? Also, you need to, for the cheat sheet, you need to submit it at the end of the exam. Okay, let me clarify that. Okay, so do you see that? You also need to submit your A4 paper along with the exam. Okay. Is there any question, comments about the midterm exam? Some of you, especially with change of major, may have exam conflicts, right? So makeup time have been arranged by IC. Okay, so talk to IC. Any question, comments about the exam? Any question, comments about the midterm exam? Okay, if not, let us continue a little bit with queuing theory. Okay, before I let you do an essay problem on queuing theory as a practice, and then I post more practice midterm problems. Okay. So the question is, oh, you mean the exam quizzes, right? So I would say depend. Okay. Some quiz problems in the exam may be more tricky or uh, a little bit more difficult, but many of them are also following the same flavors as the quizzes that you've been doing every week as well. Okay. But of course, the essay questions are more extensive. Any other question about the midterm exam?
Excuse me, Professor, you there?
Yeah. Yeah.
Would there be calculation, especially on the regarding the queuing?
How can there not be? Because I taught you how to calculate things.
I mean, is it like choice or is it like a essay and like we have to like show our work?
For the essay questions, you have to show your work, definitely. For multiple choice questions, for the queuing theory, you just need to select the correct choice.
So there will be calculation in the essay. Is that correct?
Yeah. Why? Otherwise, why are they called essay questions? For the queuing and maybe for the other question as well.
Thank you, Professor.
Yeah, no problem. Okay, any other question? Okay, if there is none, okay, let's continue. We have just a little more to go. Okay, so let me pause the recording. Okay. Okay, let us recall ourselves that we finish with some queuing systems, right? MM1 in particular, right? With only one server and infinite queue, right? And then we move on to a finite queue, right? But still with one server, right? And because of this finiteness of the queue, and hence the system, you see first time in this MM1K queuing system, the possibility that an incoming customer will be rejected, right? As a consequence, in the use of the little formula, you need to modify lambda to effective lambda, right? Accounting for the chance that an arriving customer could be rejected, right? And then we see the behavior of the MM1K queuing system as the queue capacity increases. Okay. And then we provided some concrete example of the MM1K queuing system. Okay. Today we introduce one more complication going from one server to multiple servers. Okay. So to that end, we start simplest with the queue with no limit, right? So here is an MMC queuing system with C servers instead of one server, but still there is no limit to either the queue or the system, right? So it's like MM1, except that instead of having just one server, now we have C servers. Okay. So if you look at the state transition diagram, right? Again, it will go on forever because there is no limit to the system, right? Now we just have to figure out the transition rate, right? Because the arrival rate is still Poisson, right? And all the service time distributions are memoryless, namely exponentially distributed. Let's say with rate lambda and mu for the individual server. You would expect that there would be a lot of similarities between this queue and the MM1 queuing system, especially for the arrival part, right? Because for the Poisson arrival, customers are arriving independently, right? So how would you expect the transition rates of this queuing system to be similar to MM1 queuing system, and to also be different, right? Some have to be different, right? Because you have C servers instead of one server. So which parts do you think will be the same, and which part do you think will be different from the MM1 queuing system? Can anybody tell us, maybe? Is it the arrival transition rate or the departure transition rate that will be the same as those in the MM1 queuing system? Which part do you think will be the same? I would argue the arrival, right? Because of the fact that the customer they arrive individually, right, in a personal manner. So that's why you see that the only dominating probability is either in a small interval there is no arrival, or if there is any arrival, there is only one, right? And that increment of one happens at the rate lambda, right? According to the arrival process. So the question now is, if the arrival rates are exactly the same as the MM1 queuing system, then the departure rates have to be different, right? And I can tell you the answer right away, that for the MMC queuing system, the departure rates are like that. But why, right? What is the observation that you can make about the departure rates, the transition rates of decrementing in the MMC state diagram? What type of observation can you make? It starts with mu. Next one is 2 mu. And it keep increasing, right? With 3 mu. But does it keep increasing forever? No, right? It is capped at C mu. Can anybody tell me why it's capped at C mu? And why it has to start with mu instead of starting from C mu directly? Can anybody give us some justification of this transitioning rates down? How can you think of the so for the arrival process, right? You can think of the inter-arrival times, right? And it will be exponentially distributed according to the exponential distribution with parameter lambda, right? But what about the service time for the MMC queuing system? How can we think about that? Can anybody guess why the transitioning rates now are following this pattern? How does it look for the MMC queuing system? So remember, in the MMC queuing system, right? Here, as the customer are arriving according to the some process, right? There's a single infinite queue accepting the incoming customers. But now, instead of one server, we have C of them, right? One up to C, right? So, but we also specify the service times of individual servers, right? So what what is that service time? What is that service time distribution? So let's say, let's call it tau 1, tau 2, up to tau c, right? So how are they distributed? They're exponentially distributed, right? Because of the second f. And also they are identically distributed, right? But because the servers are independent, all these service times with tau 1 to tau c are mutually independent, right? So what can you say about this collection of service times across different servers? So at any particular point in time, let's say all the servers are occupied. So I'm at the state C, right? So there are customers at all the servers, okay? And because the total number of customers is C, there is no one in the queue, right? So now at this point, here I'm at C. I already know the transitioning rate up is still lambda, but how can I argue that this transitioning rate is C mu? With the knowledge of the joint distribution of all these service times across all the servers, how does C mu emerge? Can anybody recall an important property of a collection of exponential random variables? So let me ask you this, okay? Let's say we start the clock at time 0, right? Where all the servers are serving some customers. The service times are tau 1 and tau c, which are mutually independent and identically distributed as the exponential random variable with identical parameter mu, right? Then, because we interested in this transitioning rate down, okay, from C to C minus 1, what is the time instant that there is a transitioning rate down from C to C minus 1? What is that time instant where the system go from C to C minus 1? Going from C to C minus 1 means the fastest server finishes with each of the customer, right? And that can happen at any server depending on the sample part we're talking about. So as you can see, this transitioning from C to C minus 1 happens at the minimum of tau 1 up to tau c, right? Can anybody recall what is the distribution of this minimum? What is the distribution of this minimum? Can anyone recall the distribution of this minimum? Remember, each is exponentially distributed, right? With parameter mu. What should be the distribution of the minimum? If you don't recall, you can go back maybe when we talk about exponential random variable, remember? In the service mechanism, right? Remember this exponential uh, random variable, right? Satisfying the memoryless property, right? And remember, we argue that the minimum of two independent uh, exponential random variables is also exponentially distributed, right? With the parameter being the sum. Remember that? And then we extend it to minimum of any collection, right? With more than two constituent exponential random variables, right? And then the resulting minimum will also be exponentially distributed with the parameter being the sum of all the constituent parameters, right? As a consequence, if each constituent random variable is identically distributed with parameter mu, right? The minimum will be with parameter k mu, right? Remember that? Okay, so that's how it happened, right? Because of what I just discussed about the about uh, the effective service time when you have C servers being the minimum of how one, how C, right? Because this is a time instant where there is a transitioning down by one, right? It doesn't matter which server gets done with his or her customer. That customer will leave the system and the system will go down by one, right? Okay, so now that we prove this transitioning rate down, what about these rates large form the node larger than C? And what about rates going down from the nodes lower than C? How come these rates remain constant, but these other rates are going down? Can anybody explain? You can argue by the same token, right? Because we get to see mu because when there are C customer, right? All the servers are being occupied, right? And as a consequence, when you take the minimum of all the service times of all the customers serving some customer, there are C constituent service times, right? But if they are lower than C, for example, there are two, right? Then even though there are server, okay, at this state, right? Only two servers, let's say 1 and 2, are serving customers. The other server are serving none, right? So when you take the minimum, it's only between two service times, right? So that's why you see the factor 2 emerging according to the current state, right? So for 1, it's only 1 mil. For state 3, it will be 3 mil accordingly until you reach C mil, transitioning down from state C, right? And by the same token, you can understand why starting from C, this transitioning rate down remain constant as C mil, right? Because there are only C servers, right? This minimum will never be between more than C service times, right? So that's why all these transitioning rates remain fixed as C mil, starting from transitioning down from state C. Is there any question, comments? Okay, if there's no question, then after we figure out all the transition rates, then we just need to play the same game, right? Deriving the global balance equation at each state, okay, by calculating the total flow going out to be equal to the total flow coming in, right? So the change that you see from the MM1 queuing system are these coefficients, right? Okay. But again, you can still do the same health cancellation, right? So, for example, uh, this one you can cancel with this one in the second equation. This one, oh, sorry. I mean, from the first equation, right? You can use the first equation in the second equation to cancel the two terms on both sides. Then again, you can use the modified second equation on the first state, okay? Cancel the corresponding terms on both sides on the third state, right? So on and so on. So what are you left with? You are left with this type of progression, right? Which is similar to MM1 queuing system, but there would be increment in the coefficient on the right side, going from state 0 to C. and these coefficients will remain fixed starting from state C on, right? So the geometric relationship is no longer fixed like the MM1 swing system, right? But now here there are two phases, right? There are phases. There is the phase in which the arithmetic coefficient would increase, and then there's a phase in which the rate is fixed. So if you write down the relationship, okay, where you define A to be lambda by mu and rho to be lambda by C mu, you can get the relationship of these stationary probabilities according to this equation, right? So starting from PC, which is A to the C, C0, C factorial, subsequent P's are geometric to PC, right? With a constant rate being rho. But before that, you see this type of relationship with factorial in the denominator. But these are still stationary probabilities, right? So they have to sum to 1, right? So using this fact, you can solve P0 in terms of these parameters. And once you solve for P0, you can substitute it back to get all the P's. Okay. So in the context of MMC giving system, right? There's an important parameter related to the wait time, right? Because there are C servers, right? And arriving customers will only have to wait if all the servers are being occupied, right? Otherwise, if n is less than C, then the arriving customer will not have to wait. So that's why for the MMC queuing system, it's imperative to derive this probability, right? And what is that probability? You just sum up all the P starting from PC, right? And you know that conform to the geometric relationship, right? Starting from PC instead of P0, like in the MM1 queuing system. But because the sum of these geometric terms is also 1/1 minus rho, get this formula. So this is the probability that an arriving customer has to wait, right? Because in the complementary event, any arriving customer will not have to wait. It can go directly to be served. Okay, that's why for the MMC queuing system, This is an important parameter defined as a function of C and lambda over mu, right? According to this formula, where C is this formula as a function of P0, which you can solve for, which you obtain from this formula. Right? So everything is a function of lambda, mu, and C, which are the full parameter set of the NMC queuing system. Okay. Now that we derive all the stationary probabilities, okay, we can use them to compute many statistics, right? Something like if, for example, can use all the stationary probabilities to compute the expected of number of customers in the queue, right? So again, recall that with less than C customers, right? All the customers can go to be served directly, and none of them will be in the queue, right? So if you compute NQ, you only have to start from PC, right? And of course, for N larger than C, right? C of them will be served, right? And the leftover, which is N minus C, will be in the queue. So that's the value in the computation of the expectation, right? So you get that same progression again, sum over A rho to the K, right? Times P of C. That is P of C rho divided by 1 minus rho square, right? You can write it in terms of CCA that you define already. That is PC divided by 1 over 1 over divided by 1 minus rho, right? So you get expected number of customers in the queue in terms of the system parameters. Okay. Having computed the expected number of customers in the queue, we can use little formula to compute the wait time. Remember, this is the little formula applied only to the queue, right? And now, again, because there's no limit to the system, no customer is being rejected, right? So you just have to use the original lambda in the little formula. So here you have the single queue and you have C servers, right? But instead of applying little formula to the entire system, now you only apply little formula to the queue. Right? And as a consequence, you get that the time in this sub little formula is only the time in the queue, that is the waiting time. Right? For the total time in the system, right? Because each customer will be served by only one server, right? With the service time being exponentially distributed with parameter mu. Right? So you just need to add 1/mu to the wait time, get expected total time in the system. Right? Having compute expected total time in the system, now you can use the little formula in the other direction for the full system, right? Get the expected total number of customers in the system, both in the queue and at the servers. So you basically multiply this by lambda. First term, we get given queue. Second term, lambda over, right? Okay, any question, comments about the MMC queuing system? It's quite interesting to use the knowledge of MM1 and MMC to look at realistic trade-off between employing more servers, okay, that are potentially slower, compare that with maybe certain systems with fewer servers, but are faster, right? Because faster servers means they're more expensive, right, than slower one. So you can trade that off by if you want to use lower servers, you can trade that off by using more of them. Right? So let's make this study more concrete by consider queuing system representing maybe an IT company that are considering two choices of employing just one server that works very fast. Compare that to the other choice of employing two servers, each being slower. Okay. In particular, for real situation, there could be more than two choices, right? So in this case, we can consider three choices, right? One, this one is only one supercomputer. So it's like the MM1 queuing system, right? Where the single server is very fast, right? That come with this rate of 16 tasks per minute. An intermediate choice may be using less powerful mini computers. You can see their rates are slower, right? Because of that, they're cheaper and you can afford to buy more of them. So in this case, depending on the price, let's say you can deploy 2 of them, right? Notice that 2 times 8 is equal to 1 times 16. So in that sense, you consider the product of number of servers and their rates. These 2 choices are kind of comparable. But of course, in realistic situation, you have to consider their prices. And then the last option goes with the slowest type of computer, personal computers, okay, which are even less expensive than mini computers, right? And cheaper. So now you can deploy even more of them, right? So this second choice is like the MM2 queuing system. This last choice is like MM6 queuing system, right? Now that we consider MMC queuing system with an arbitrary C, we are in we have the knowledge to compare these 3 choices, right? Okay. So the first choice is like the MM1 queuing system, like C is 1. So of course, the arrival rate remains fixed. The service rate is the fastest, and in this case, rho is a half. Using the calculation that we have done for the MM1 queuing system, we can compute the total time in the system and the wait time in the system to be according to these numbers. Okay. In in minutes. Okay. As for the second choice, you see mu is lower, right? But there are 2. So it's like MM2 queuing system with A being 1 and rho, which is lambda by 2 mu being a half. Right? So you can use the formula that we derive to compute the probability that the system being empty to be 1/3, the probability that there will be 2 customers be 1/6 is critical parameter that the arriving customer doesn't have to wait to be 1/3, right? And you can also compute the expected total time each customer spend in the system and its wait time, expected wait times. So what do you observe when you compare it with the MM1 queuing system? This is for the MM1 queuing system. So the wait time is about 0.06 minutes, and total time is about 0.12 minutes. For MM2, you can see that the wait time is shorter, right, than MM1 because there are more servers, right? Um, um, there's more chance that when one server is occupied, you can go to the other server, thereby reducing the wait time. Right? But because each server is slower than the one in the MM1 queuing system, including the service time, the total expected total time become longer in the MM2 queuing system compared to that in the MM1 queuing system, right? And you can expect the same behavior when you add more servers. So you can see there's even more reduction in the wait time. Okay, that is beneficial to the customer, but at the same time, the expected total time would increase as well. So depending on how you measure the customer frustration, if they hate to wait uh, idly, then they hate that the service is too long, then you may want to go with the last option. On the other hand, if customers get frustrated easier, if the service is taking too long and they don't mind too much, a little wait, then you may want to go with the first option of MM1 queuing system. Any questions, comments about the MMC queuing system? Okay, do you need a break? Do you need a break? Okay, so the last one that we will study, okay, is putting a more realistic constraint into the MMC queuing system by adding its limit. Right? So in this case, here we assume that the limit to the system is equal to the number of servers. So what will be the consequence of that? So typically what you see is that this number is at least C, right? Because the fourth number is the limit to the total customers in the system, right? So that's including C at all the servers and some in the queue, right? But here, if we put the same number in the fourth character as in the number of servers, what will happen? Okay, let's see what will happen. Okay, again, as when we consider the MM1K queuing system, right? Now, with the limit to the capacity, there will only be C plus one states, right, in the state diagrams. And what will be their transitioning rates? Again, for the arrival process, nothing changes, right? Because it's still performed with parameter lambda, right? And by the same token that we discussed, for the transitioning rates down, okay, we get that these rates are C mu C minus 1 mu going down to mu, right? Because each one is arriving from the minimum of tau y, tau c, right? Similarly, this one is the minimum of tau y, tau 2, tau 3, right? So with this, now you can write a finite set of global balance equations and do the same cancellation, right? So now the this system of equations seem to be simpler, right? Because there are only finitely many equations with only one type of relationship, right? That govern all the probabilities that you can use to derive P0 and all the P's. Okay. So similar to in the MM1K queuing system, where because of the limit to the system, right? Unfortunate arriving customer can be rejected. Here, for the MMCC queuing system, when will the customer be rejected? Only when the system is full, right? So that's why for this MMCC queuing system, it's imperative to derive this probability, right? Because that will have to be used in deriving the effective arrival rate, right? Because you have to offset that, right? Because those arriving customers that come in when the system is full will be rejected. And you have to use this effective lambda in the Little's formula instead of the original lambda. So now this going back to my original question about what is so special when you put the limit to the system to be exactly equal to the number of servers. What can you observe in the application of this full Little formula? What do you see? What strange thing do you see? Remember, this is the Little formula for the full system, right? This is Little formula for the entire system, right? So this will be lambda minus lambda effective, right? Because these are the rate which customers are rejected, but the one that get through is the effective number. But again, because this is the whole system, n is counting everything. But what is the strange thing that you observe in this little formula? Is this part, right? Why is it only tau and not capital T? precisely because the limit is exactly equal to C, right? That means you get rid of the Q, right? There is no Q at all, right? Because um, if not all servers are occupied, uh, then the arriving customer will go, we can go to the serve, right? And when all the customers are being served, right, it's already full, so there can be no one in the queue. So as a consequence, no customer has to wait. That's the special thing when we make the limit equals to the number of servers. Okay? So you get this relationship about the expected number of customer in the system in relation to the expected service time, which is 1/5, and this is lambda effective. Okay. Okay, you can verify that everything is consistent, okay, by deriving this expected number of customer in the system in a brute force manner from the stationary probabilities, okay, and you can double check that they do coincide. The questions, comments? So here to conclude our discussion for queuing system, I just want to let you know that you can make your study for queuing theory a little more concrete, right? By writing simulation program, let's say in MATLAB, right? To verify your knowledge, okay? So here you can see this is a MATLAB script to simulate the MMCC queuing system that we just studied, right? So here you can define the relevant parameter, right? Mean inter-arrival time. What is that? What is mean inter-arrival time? What is the mean inter-arrival time? This is, in our notation, this is like 1 over lambda, right? And what about mean service time? That is like 1 by mu, right? So as a consequence, rho is lambda over mu, right? That's mean service time divided by mean inter-arrival time. Okay, unlike in our analysis where we look at an arbitrarily long horizon, right? Where there are infinite number of customers. For the simulation, you can do it only for finitely many customers, right? So, and this is the parameter here. You want to simulate the system for how many customers, right? Number of servers, this is C in the MMCC queuing system. And how do you simulate things? So basically, you write an simulator based on the event-based concept, right? Starting system time at time 0, right? And then simulate the arriving customers according to the croissant process, right? Keeping track of how many customers have arrived, right? Of course, start from 0. And out of those arrived customers, some will be simulated to be departed, right? According to the uh, uh, service time mechanism, right? And because here is an MMCC queuing system with capacity limit, right? Some users will be blocked, right? And basically you can keep track of all the significant events in the simulation by looking at the subsequent arrival times and also departure times, right? So the departure times are kept track in this array, right? With number of server elements, right? And the last element in this array will keep track of the subsequent arrival time, right? So that's why every time there's an update, right? So here you start off from system time being 0. So you use this exponential inter-arrival time distribution to simulate the first arrival, right? That's why you see the parameter here related to lambda, right? At the beginning, there's no customer yet, so all the server statuses are set to 0. When some are 1, it means that those servers are occupied, right? And you do the simulation until this number is reached, right? And basically, you do the simulation using the event-based principle, right? Every time keeping track of the next important event, right? That could be either a new arrival or the earliest departure among all the customers that are being served, right? So you take the minimum, meaning you want to look at the earliest next event, right? If it's an arrival, then the index of that minimum would be uh, the last one, right? Because that's how you define this element of the array here, right? So if the next arrival happens before any of the departure, right? Then you just increment the number of arriving customers, right? And simulate the subsequent arrival time, right? Okay. On the other hand, if one of the departures happens before the new arrival, then you increment number of departing customers, right? And then set the status of the corresponding server back to 0, right? And do this cleansing of this array, keeping track of the next earliest incidents. So just to illustrate to you, okay, in the MMC queuing system, there's a theoretical quantity called the blocking probability, right? That's the probability that the system is full, right? Which you may recall that it is given by this formula. Let me go back to MMCC queuing system. So you can see this blocking probability, right? For the MMCC queuing system. Right, which is defined to be the probabilities PC, right? PC is this, right? So rho here is like the parameter A that we define, right? So PC is A to the C divided by factorial C. And the denominator here is this part, right? Because P are all the probabilities in the stationary distribution, right? So that's in theory. In simulation, right? You can just numerically compute how many customers are blocked divided by the number of customers that have arrived, right? Okay. So let's see how the simulation goes. So here I'm using lambda equal to 1, mu equal to 1/5, right? So let's run it a little bit. So you can see yeah, there could still be some difference, right? Because of the fact that we can only simulate a finite number of customers, right? But you could expect that as you increase the number of customers to be simulated, right? This difference can be reduced, right? So you can see if I increase it 10 times and I do the simulation again, then the variation would be smaller, right? So this one is from the theory, right? So this is a constant, whereas this depends on the random numbers for each simulation, right? So you see this number, this blocking probability, simulated blocking probability keeps changing for every run, right? But if you increase the number of customers to be simulated, eventually you should get very close to the theoretical number, right? But on the other hand, yes, so now you see with 100,000 number of customer, I start getting to the same number now, right? but it's also taking me longer. Okay, so let's run it again. Okay, sorry, let me run it again from the start. So you see, there's still some variation, but you see a smaller one with increasing number of customers. Okay, and the code is fully given to you in the slide here. You can try it yourself. Okay, so if you more comfortable with plots than just numerical simulation, then we also give you another simulator that can display you the staircase plots as well. So here, right, again, it's for the same MMCC queuing system. Okay, you can see the same type of parameters, right, same type of variables, but here we will plot things for you as well. Okay, so let's see how it goes if I run this one with uh, the simulator displaying also the staircase plots. So you see, in addition to just the numerical values of uh, the display variables, so here this simulator also show these important staircase plots, right? So what are they? So in this case, is MM 1010 queuing system, right? M/M/10/10. I only simulate a few number of customers here because I want you to clearly see the staircase plots. Okay, of course, at the top of the staircase plot, that is the one with the largest quantity, is counting all the arrivals, right? The other plots cannot exceed this, right? Because if there are no arrivals, then the other ones cannot be incremented, right? Okay. And of course, as the system progresses, you see that some customers would have departed, right? That's shown in green. So the difference, of course, are what? Either in the system, right? Or in this case, when the system is capacitated, some could be rejected as well, right? That's shown in red. Okay. So here, the system limit is 10, right? So that's why you see that this magenta staircase plot is never going beyond 10, right? Because that's the system limit. But when the departure rate is slower than the arrival rate, okay, because the system is capacitated, some could be rejected, right? So basically, when there are rejection, you see that the difference between the blue, right, and the green, let's say here is 21st, right? And if you look at here is what? 21st and 13. In this case, there's no rejection, right? Because the difference is only 8, right? So you see eight customers here, and there are no rejection. Okay. But when the arrival rate is faster, let's say here, maybe, or here, right? Maybe here 27 against 16, right? So that means one customer is rejected, right? See, one customer is rejected and 10 left in the system. Right? So that's why you see that the magenta plot is never going beyond 10, right? Of course, if you want the calculated numerical value to be more accurate, you have to again increase the number of customers to be simulated, right? But it will be harder to see the staircase plots as well. So like here, instead of 20, if I simulate for 10, 100 customer, you can still see the staircase plots, but the resolution will go down, right? Okay. Any question, comments about these simulators? Okay, again, if you want to more information, okay, you can consult these references. The main one would be this book, right? It has gone to the 3rd edition now. There's a chapter related to queuing system, okay? Other than that, okay, you can see in the syllabus that there are other references, right? This one in particular for the introduction chapter, okay? This one especially for mobile and cellular networks, okay? And also a little bit of 5G, but there are some extra materials about 5G in our 5G slides than in any of these references as well. Okay, but if you understand the lecture slides and all the lectures, I mean recordings well, okay, you should be in good position for your midterm exam. Okay. Okay, that will conclude our discussion of the final topic before the midterm. Okay, so if there is none, okay, I will post one essay question for you to practice. Okay, please do it before the end of the class. Okay, so that you can have some practice for the upcoming essay question. In addition,
Would
I
this be,
post. Pardon?
excuse me, Professor?
Yeah.
Well, would this be graded? I was a little busy and I might not be able to like make it to the end of the class.
Then do it quickly. You can do it in 10 minutes. Okay.
All right, fine. I'll
Yeah.
try to find
Okay.
time. Thank
Just
you very
one
much.
question. Yeah. Okay. And then this last one is practice problems for your midterm. Okay. They are all multiple choice. Okay. So you can see some There may be some repetition with some older quiz problems that you have done. Okay. But at least you get some flavor of what will be on the multiple choice questions for the exam. Okay. So again, I stress that there would be 45 questions for the midterm exam. Okay. 38 multiple choice, 7 essay questions according to this distribution. Okay. Totaling 100 points. Oh, sorry, essay question. I think I make a mistake. It's not 10 point each. This one is 62, right? 62 points total. Yeah, total. Yeah. Okay, 62 point totals. Okay. This one 38 point totals. Okay. So totaling 100 points. Please prepare your cheat sheet. Okay. You can write notes only by hand on both sides of your A4 paper. In addition to that, you can bring one non-programmable, non-graphical calculator to the exam room. Oh, sorry, I forgot to share maybe. This one, okay. You can bring one non-programmable. Okay. Non-programmable calculator into the exam room. Important to bring a ruler and a pen as well, in addition to other stationery. Okay. And write legibly, favorably with a pen, right? So that does not fade. Okay, if there is no further question, good luck with your exam. And please do this one before the end of the class. There's only one question. You can do it very quickly. Okay. And this one is good for you to do as soon as possible, but I think this one might not be graded. Okay. Because there may be a lot of repetition with what you've done already. Okay.